Welcome to Part E on this very long chapter on quality control. So in the previous part, we took a look at our first type of attribute data, and we did a P-chart with that. In this part, we'll take a look at the other type of attribute data, and we'll do a C-chart. So again, the two types of attribute data. Type 1 binary, it's either good or bad. So we had defective stakes and good stakes. There was only two types. Type 2 is when we have several different types of things that could go wrong. And what we're going to be doing is counting how many things did not go correctly or how many defects that we had. So for type 2, type measurement counting defects, the C-chart is what we need. Now, sometimes students have difficulty in identifying a C-chart problem, and there's usually a kind of a dead giveaway to help students. So as a little tip in exam problems and also homework problems, whenever you see the phrase defects per, that is a dead giveaway that this is a C-chart problem because there's several types of defects that could occur, and it's listing how many defects per whatever it is that we are measuring. For example, if it's a car, how many defects per car? So what we'll do is we'll apply this to our example of Deluxe Super Steakhouse. So the third most important customer requirement from my customers was the courtesy of the wait staff. So I need some way of kind of measuring how well we're doing in that regard. So all of the waiters and waitresses in my restaurant are going to be trained, and one of the things that they will do when they first approach a customer's table is to introduce themselves, ask if they had ever been to Deluxe Super Steakhouse before, take the customer's drink orders, describe any specials of the day that we might have, and then finally give the customers the price of specials for the day. And if you think about it, you go to most restaurants, they'll do the first four, but they won't tell you how much the prices are for the specials unless you specifically ask. But in my restaurant, we're going to let people know what things cost. So other examples of C-charts could be things such as this. So scratches and chips and dents per car, okay? Bacteria, each one of these you can see that there is a per unit involved with this. So many defects per something. So every time you have something like this, it's basically a C-chart problem. Now, there's only one variable in a C-chart, and that is the variable C, which represents the count of the number of defects per unit. So if you've been measuring things for a long time, been making cars, for example, for a long time, we know on the average car has so many defects in it when it comes off the assembly line. That would be your C. But if the process is new, if you do not know what that average is, then we can have an estimate for C. This is very similar to what we saw in the previous part where we were making an estimate of our percent defective. So that's what we're going to be doing here. We're going to be making an estimate of our C. C bar is defined to be the ratio of the number of defects divided by the number of samples. Now, that denominator sometimes throws students a little curveball, the number of samples. Now, we're not talking about sample size now. We're talking about samples. So here's the data from the case study. So I had my head waiter conduct a survey of customers who were leaving the restaurant and just asked them some questions to see if the waiter or the waitress had done everything that they were supposed to do. So on Monday, out of all the customers that the head waiter talked to, he found that there were 3 instances where there was an omission of data. That is, there were 3 tables where all the information was not given. On Tuesday, there were no omissions. That is, all the tables, all the customers, all the information was given to them. Wednesday, there were 4 omissions. On Thursday, there were 5 omissions. And on Friday, there were 2 omissions. So our counts are going to be 3 for Monday, 0 for Tuesday, 4 for Wednesday, 5 for Thursday, and 2 for Friday. So what is the value of C bar? And calculate the 3 sigma control limits and determine if the process is in control. So these are my counts, and the number of samples each day of the week represents a sample. So Monday is a sample, Tuesday is a sample, so the total number of samples in this example is 5. So the sum of all the defects across the week is 14, and there were 5 samples, so there was an average of 2.8 defects per sample or per day. And again, we want the Z value in our formula to be 3 because the problem requested a 3 sigma control limit. So here is the formula for the C-chart control limits. It's equal to C or C bar plus Z times the square root of C. And the lower control limit is the same except minus Z times the square root of C. So we know that C bar is 2.8. We know that Z is 3. We can calculate the upper control limit to be 8 defects per night. The lower control limit will calculate to be negative 2.2. Now, once again, is it feasible to have a negative number of defects? If you think about that, the answer is no. So once again, if the lower control limit, just like on a P-chart, is a negative number, you're going to convert that negative number to the lowest feasible number that you could have, and that would be 0 defects. So now that we have our control limits defined, we can draw our control chart, plot our data. So we have our control charts here. The data that we're going to plot is going to be our C data, our counts, and we will draw our conclusion. Now notice that on Tuesday that the count fell exactly on the control limit. So we have to put our thinking caps on here and really remember what we're doing, what this represents. On Tuesday, we had no defects. How could there be any problems if you have no defects? So for the C chart and also for the P chart, both of these charts, what you're really more interested in is any data points that fall above the upper control limit. The lower control limit, if something fell below the lower control limit, that's not a sign of something bad going on. That's actually something good. So if, for example, the lower control limit in this case turned out to be 1 defect, and we had a day where we had 0, would we conclude that the process is out of control? That wouldn't make any sense to do that. So our conclusion here is that all the data points fall within the limits and the process is in control. And the randomness, the variability is the result of randomness. So now that we've gone through all four of the control charts, the X-bar and the range chart, let's kind of summarize a little bit each of them. They each have a specific purpose. So the X-bar chart, its purpose is to detect any changes or shifts in the mean or the average value of the process. The range chart, its purpose is to detect any changes in the dispersion of the data. So is the data becoming more spread out, the measurements? Another way of saying dispersion is the standard deviation. The P chart, its purpose is to detect changes in the percent defective in the process. And the C chart, its purpose is to detect any changes in the average number of defects per unit, whatever the per unit could be. It could be per car, or it could be per cell phone, or whatever. So I want you to be able to know what the purposes of all four of these control charts are. And you will see several questions on the exam where you will need to know what these are. And then finally, as a reminder, what type of data am I going to be plotting once I have my control limits for each of these charts? So if I'm doing an X-bar and I have my control limits, the data that I'm going to plot is the X-bar data, or in other words, the sample, the mean value, the average value of each sample. In the range chart, the data I'm going to plot is the ranges, the difference between the highest and the lowest value. A P chart, the data I'm going to plot is my P values, my percent defective. And in the C chart, what I'm going to plot on that is my C's, that is the number of defects that I counted in that particular sample. This will conclude this part of this chapter.